This is the setup for the conservation of energy experiment. Before starting the experiment, there are a few settings that you need to do on the program. First of all, when you open the program, you'll see a graph of force versus time, and then the graphs that we always see, which are position versus time and velocity versus time. And the reason is that we have the force sensor connected in this experiment. That's why we have the force versus time displayed. And we also have the motion detector connected, so you have the velocity and position versus time graphs for this reason. The first step is to allow the program, or to let the program record the force as a function of a variable that you will enter. Okay, because your task in the first part of the experiment is to compress the spring by some distance. Okay, let's say for example, I'm going to compress the spring by 1 centimeter, and then tell the computer that this distance is 1 centimeter, and then also acquire or obtain the reading of the force at this position from the force sensor. And then we'll change the distance to 2 centimeters and then record the reading of the force sensor, and so on. So for this reason, we will change the mode of operation of the program into something called events with entry. Okay, the event being the force on the spring, and the entry is the value that you enter for the distance. So I'm going to click on experiment and then data collection. And then here you can see that the mode of operation is the time-based, which means that the program will collect data for a specific time interval, which is 10 seconds in this case, and then stop. So this is what we always use, but in this experiment we'll change it to events with entry. Now, the entry name, or the column name for this entry, I will call it, for example, change in distance. I will type change in distance, and the short name, let's call it for example delta x. So I'm going to click here to access the upper Greek letters and then use the delta and then x, and the unit I will enter x in meters. Done. You can see now that we have now the force versus change in distance instead of force versus time, because of the change that we did for the mode of operation. Furthermore, in part 1 of the experiment, we don't care too much about the position or velocity versus time, so I'm going to increase the size of the force versus change in distance so that it is displayed on most or all of the screen. Now, if you look carefully, you'll see that whenever you push on the spring, the force displayed by the force sensor is a negative value. Okay, we want this force to be a positive value. So for this reason, we have to reverse the sensor. So I will go to experiment and then set up sensors, show all interfaces, and then here is the force sensor again. I'll reverse its direction. Okay, now when I push against the spring, the force displayed is positive, and this here is the force by the spring, not the force on the spring. Okay, so now the force displayed is the force by the spring, exerted by the spring on my finger or on the card. To start collecting data for part 2 of the experiment, I'm going to click on collect and just keep it running like this. Now the cart is not resting against the spring or not pushing against the spring, and the force exerted by the spring is 0 in this case. Okay, so I'm going to keep this point. This is my first point. The compression in the spring is 0 and the force from the spring is 0. So this is a useful point. So I'm going to click on keep, and it will ask you what is the distance in this case, or change in distance. It's 0 because I'm not compressing the spring. And then click OK. So this is your first point, and now it is stored here by the program. The next point is when the spring is compressed by 1 centimeter. Now to find out this distance accurately, take a look at the edge of the cart and make sure that you are looking vertically. The edge of the cart is at 103.8 centimeters. So to compress the spring by 1 centimeter, this edge of the cart has to go to the 104.8 centimeter, right here. And to hold the cart, we recommend that you hold your finger against the track itself. Just push against the track. This makes it steady. And then this is my second point, so I will click on keep. This time the distance is 1 centimeter, so I'm going to type 0.01 because we need it in meters. Okay, and then click on OK. So my second point is stored. So I'm going to move to the third point, which is a compression of 2 centimeters. So I'm going to compress the spring by 1 more centimeter. Again, watching the edge of the cart, make sure it is where it should be. And then click on keep. Now my compression distance, it's 0.02 meter, which is 2 centimeters. And then finally, you move on to the fourth point, which is 3 centimeters of compression. Now I'm done collecting the data, so I will click stop. Pay attention to this because it's a common mistake by students to stop after every reading. Stopping after every reading will erase the reading when you start again. Okay, so you have to take all of the readings, and then after you're done with the 4 readings, you stop the program. And then if you rescale, you'll see a line representing your data. Okay. Now 2 things are required from this graph. This is a graph of force versus change in distance, or F versus X for a spring. Okay. First of all, you'll need the slope of this graph. Okay. So you'll have to add a linear fit to this graph. So I'm going to highlight the whole graph and then add the linear fit, because the slope will be used somewhere in this experiment. Okay. Furthermore, we'll find the area under this graph. Okay. So I'm going to highlight the whole graph, but you'll need to find the area from 0 to 2 centimeters under the graph. You can tell here that my graph is not complete for the purpose of the demonstration, but in your case, your graph will extend to 3 centimeters, okay, and you'll only highlight the area between 0 and 2 centimeters. All right, so I'm going to click on this symbol which says integral. This will evaluate the area under the graph. Okay, and here it will tell me exactly how much area is under the graph. You can tell here that from the unit it says Newton meter. Okay, Newton meter is a confusing unit. We know that the area under this graph should represent the energy. Okay, the program doesn't know that we are calculating energy. It just tells you that the area is the unit of the y-axis multiplied by the unit of the x-axis. But when you report it, you should write it in joules, because commonly in physics we use Newton meter to represent the torque. Okay. The slope, on the other hand, has a unit of Newton per meter, which is the y-axis divided by the x-axis. Okay. Now this slope represents the spring's constant. All right. The spring's constant can be used to find the energy stored in the spring in several configurations, as you will see in your lab report. To do part 2 of this experiment, we have to cancel the settings that we did. Okay, so I'm going to close the program. This is the easiest way. Just close it without any saving and reopen it. Here's Lagar Pro again. And as you can see now, it displays again the force versus time, position versus time, and so on. Now in part 2, the graph that we want to consider is the velocity versus time. So I'm going to hold it and maximize it so that it is displayed on most of the screen. Now in this part of the experiment, note that because I closed the program and reopen it, the force sensor is displaying a value again, but we don't care about it because we're not reading the force. Okay, so you don't have to reset the sensor. So I'm going to compress the spring by 2 centimeters again by watching the end of the cart, looking vertically. So in my case it's at 103.8. I will compress the spring by 2 centimeters so that the edge of the cart is now at 105.8, and then start the data collection. Note how I am holding the cart, same thing. I'm holding my finger against the track to make it tight and stable, and then I will click on collect and release. Now, as you can see, the velocity in my case is negative. So you can either work on this as it is, or if you don't like it, you can reverse the motion sensor. So let's reverse it to show you how it looks like with the sensor reverse. So I'm going to experiment and then set up sensors, show in all interfaces, and then for the motion detector in this case, I will reverse the direction. Okay, and let's repeat the experiment again. So compress the spring by 2 centimeters and then click on collect and release, and you can start the program there. Now, as you can see, the cart was at rest, and then I released the cart, so the spring accelerated the cart. And here at this point right here, the cart lifted the spring. Okay, so the cart is now moving with some velocity after it lifted the spring. So all of the potential energy stored by the spring was converted into kinetic energy right at this point. So I will highlight this point and a little bit before, a little bit after. But in this case, when you do the statistics to find the velocity, you know that you have to take the maximum value, because the maximum value of the velocity occurs at the moment the cart leaves the spring, and all of the potential energy is converted into kinetic energy. So record the maximum value of the velocity, and later on you can use it to calculate the kinetic energy of the cart.